lecture. One comment for speakers in general, this came up after the first lecture, is that when someone asks a question, it would be good if the speaker just repeats the question so other people can hear. Okay, so the second speaker of the day is Bjorn Poonen, who's going to speak about Hilbert's tense problem.
Okay, thank you. So, can you all hear me? Is it on, or it just needs to be louder? I'm speaking pretty loudly, but is it possible to turn up the volume? This is the maximum, okay. All right, so I want to start by saying that I'm not a real logician, so I'm mainly number theorist. So I encourage all the logicians in the audience to interrupt me and correct my terminology and my logic. All right, so let me start by giving you by stating what Hilbert's tenth problem is. So this is a question that Hilbert asked in a paper in 1900. So the question is there an algorithm? I'll make this more precise in a second. So that takes as input a polynomial with integer coefficients and in many variables, and outputs either yes or no. So in particular, the algorithm has to terminate and decide. Has to decide one way or the other in a finite amount of time. So if the equation f equals 0 has an integer solution. So in other words, yes, if there's some n tuple in z to the n such that f of a is 0, and no otherwise. Okay, let me first tell you the answer. Fortunately, we're living after 1970, so we do know the answer to this question, and it's no. So there's no such algorithm. So it builds on work from a 1961 paper of Davis, Putnam, and Robinson, so 1961. And then the final step was done by Matyasevich. Oops. Let's see. Okay, but in order to give a no answer to a question like this, you have to be very precise about what you mean by algorithm. And so let me clarify this. So by algorithm, I'll always mean Turing machine. And I'm not going to give a precise definition of Turing machine, but I hope that many of you know it already. Essentially, so approximately what this is, well, you can think about it as a computer program. So a finite length computer program. I don't know if people ever look at infinite length computer programs, but that's certainly not what I want. Okay. So running on an ordinary computer, whatever, like your laptop, except that it has unlimited memory, so you don't have to worry about running out of memory, and you don't have to worry about it getting hit by lightning or anything like this. So it's better than most computers available today. Okay. All right, and it accepts okay, I'll make the following assumptions. So it'll accept a non-negative integer input. Now you might well, okay, I'll fix this later. So because it doesn't look so good for Hilbert's 10th problem. Non-negative integer input, and as it goes along, it might possibly and possibly it might print some output. So it might print some characters or some numbers or to some output tape. All right, so now this is problematic because we want to input, at least for Hilbert's 10th problem, we want to input polynomials. So let me just say that if you want to have some other kind of input, that's okay as long as you fix some way of encoding those other kinds of inputs or other. So, okay, so provided that you choose an encoding of them. So for instance, if you want to input a polynomial like this into your Turing machine, you could write out some tech code for the polynomial and translate all the characters into ASCII symbols and concatenate them and make some non-negative integer. Okay, and it really doesn't matter exactly. Usually, it doesn't matter how what the exact encoding is, because at least if you have some reasonable objects and some reasonable way of encoding them, a Turing machine can easily translate between two different encodings. Okay. Yes.
Where ends the first parenthesis, because it's a computer program, you have to be careful. All the kinds of input provided. It's okay.
What was? I missed. Where is it?
You didn't close the first. Excuse me.
A finite computer program, accepting.
Close the second.
Oh, okay. All right. I knew that there were going to be some logicians in the audience. All right. So thank you. Yeah. So feel free to interrupt me, any of the rest of you, because I mean, yeah. So otherwise it gets it. Yeah, it's more interesting this way. All right. All right. So in order to say something more about this problem, I'm going to introduce some basic concepts from recursion theory. Yeah, and maybe I should have said, today I'm going to be mostly talking about this, the original Hilbert's 10th problem. Later on in the lecture series, on later days, I'll talk about generalizations where you replace the ring of integers by other rings that are of interest to number theorists. So, okay, so for now, let me define. So, okay, I guess many of the logicians probably know this already, but just in case. So, what does it mean for a subset of the integers to be recursive? So, that means that there exists an algorithm, which again means Turing machine, with the following input and output. So the input is going to be an integer. And what the program is supposed to do is decide whether or not the integer belongs to S or not. So yes, if n, so it has to decide membership. Okay, so for example, and this is supposed to be obvious. If you take the set of primes That's recursive. Now when I say a set is recursive, I'm not saying anything about how long it takes for the algorithm to make the decision. So for this, to prove this, you just have to give any algorithm to check that something is prime. Like, for example, if you want to check that n is, you give an integer n, you want to check if it's prime, first check that it's at least 2. Then try all pairs of integers between 2 and n, multiply them together, and look in that list and see if you get n. So that'll be a way to decide whether it's prime or not. I mean, it's not a very good way, but it at least shows that it's recursive. Oh, maybe I should say also, it should be clear that there are some non-recursive sets just by cardinality arguments because, well, the number of possible subsets is uncountable, 2 to the aleph naught, but the number of algorithms, the number of Turing machines is only countable since they're all described by a finite length computer program. All right, so that's one concept. So another one is, again, if you have a subset of the integers, it'll be called listable, or this is also called recursively enumerable. So these are synonyms. So that means that there exists a Turing machine, so that such that when you run it forever, S, the set S, is exactly the set of integers that it prints out. So, and when you just leave it running forever. Yeah, so Turing machines don't have to terminate. I mean, sometimes they'll end up in an infinite loop. For example, you could have the program says, well, or anyway, so for I equals 1 to infinity, print I or something. Sure. Okay. All right, and now if you want to, okay, it doesn't really matter. If you want to, you could insist that the Turing machine prints each element of S exactly once. That wouldn't change this notion because if you have a program that does this, you can always write a new program that would use this as a sort of simulate this one and watch its output as it goes along and censor the output, seeing so that whenever it tried to print a duplicate, it would just censor that and just so then you would have another. So in other words, if there exists a Turing machine that does this, then you can write another program that'll do the same thing but print out each element of S once. Okay, that's not so important, but I just thought it's sad. Okay, so the first proposition I want to prove is that that recursive sets are listable. So S in Z is listable. So this is quite easy. You can probably imagine. You can probably imagine a computer program already that's going to do this. So remember, we're given an algorithm to decide membership in S. Okay, so what do you do? So we're given an algorithm T to decide membership. And so you just construct a machine, construct a Turing machine that let's call it T prime that applies applies this membership test to 0, 1, minus 1, 2, minus 2, etc. in that order, and then well, at the end of testing each one, you know whether it belongs to S, so you just print the ones that are in S. So it never gets stuck because the membership test terminates on each input, and eventually it'll print everything that's in S. Okay, so that's pretty easy. So let me give you an example of a listable set. I'm trying not to erase at the resonant frequency of this blackboard. Okay. All right, so here's an example. All right, so let's take S to be the set of integers. So this is a number theory example. So such that it's a sum of 3 cubes. So in other words, such that there exist x, y, z integers, such that x cubed plus y cubed plus z cubed is equal to a. So the question is this recursive and is this listable? So the first thing I can say is that S is listable. So to show it's listable, I just have to write down a computer program that will print out all the elements of S. So here it is. So, well, I'm going to write in some sort of pseudo language. So loop through all possibilities for positive integer b. For each b, let x run from minus b up to b through integers. And same for y and z. And so, so these are nested loops. And in the inside, I print the value. I compute x cubed plus y cubed plus z cubed and print it. So it should be pretty obvious that all values of x cubed plus y cubed plus z cubed get printed by that program. So that is a listable set. So so then the question is it recursive? In other words, is there an algorithm that takes the integer a as input and decides whether or not it's a sum of 3 cubes? Anybody want to guess? Well, you probably don't know the answer. Well, unless you know something. What? What? Okay. Okay. So Bill McCallum guesses no. All right. So is S recursive? And as far as I know, nobody knows. Not even Bill, as far as I know, unless he has some special information that I don't know about. So but there's a conjecture. Well, maybe it's not. I'm not sure if it's actually conjecture, but in the sense that people believe it. But it's some. It might be the case that a number is a sum of 3 cubes if and only if it's not congruent to 4 or minus 4 mod 9. It's pretty easy to see that if something is, say, 4 mod 9, it's not going to be a sum of 3 cubes because cubes mod 9 are always minus 1, 0, or plus 1. So if you add up 3 of them, you're not going to get 4 or minus 4 mod 9. So, but maybe it's true that everything, except for that congruence obstruction, maybe that's the only thing that can prevent a number from being a sum of 3 cubes. So So maybe this is true. So I don't know. If that is true, then of course S is recursive because it's pretty easy to write a computer program that takes as input an integer and decides whether it's plus or minus 4 mod 9. Okay. So I just wanted to give this to just to indicate that it's not so easy to test whether something's listable set as recursive or not. Okay. So next, I want to.
Does anyone know the answer if you allow rational solutions?
If you allow rational solutions, I think what happens then is that. Okay. Mignon is asking what happens if you replace in this, you replace z by q, and ask which rational numbers are sums of 3 cubes, 3 rational cubes. That's
Or you could just replace the second z by q. Sure.
The second z. Okay, well, yeah, it's the same question. Okay, so then, yeah, the answer there is that every rational number is a sum of 3 rational cubes. The sort of the highbrow explanation for this is that this equation, it defines a cubic surface, and then the cubic surface has some rational points at infinity, and then when you have a cubic non-singular cubic surface over Q that has some rational points, there's something you can do using, well, it's similar to what you do with an elliptic curve. You can draw tangents and create new points. And it turns out that when you have one rational point, then they're automatically there's Zariski dense in the variety. So in particular, there you can find some solutions that are that are not at infinity. So you can find.
So the answer is yes.
So the answer is yes. It's recursive. In fact, it's because it's every rational number, and you can decide whether. Yeah. Okay. This, I'm not sure. I mean, I'm not sure. I think it's just that people have done some computations, and it seems whenever they've tried to find a solution, sometimes the solution has turned out to be really big, but most of the time they've found it. I mean, there might be some values of A for which they haven't found a solution yet, but they're probably just because they haven't searched far enough. I mean, I guess it's known that these are the only local obstructions. So, I mean, these are the only obstructions that come from congruences. So if you believe there's some sort of local global principle for these kind of equations, then that would imply that this is true. But nobody knows how to prove anything even close to that. Okay. So. Okay, so I want to now give you an example of a listable set that's not recursive, since that will be important in this negative solution to Hilbert's 10th problem. And this example is related to the halting problem in computer science. So let me mention this right now. So the halting problem asks, is there an algorithm that takes as input a computer program. So, and again, you can find some way to encode computer programs as non-negative integers. So you have to do that. Okay. So I'll just think of p as being a non-negative integer. And together with an integer x that's going to be fed into the program, x will be the input to the program p. And this algorithm is supposed to decide whether or not the computer program halts. So it's supposed to, the output is supposed to yes if this program, when you run it on input, when run on input with input x, eventually halts. I mean, the alternative would be that it somehow ends in some sort of infinite loop and just never stops. Okay. Okay, so it's supposed to output yes. Okay. And otherwise it has to output no. Okay, so the answer is no. So this is due to Turing. And so let me sketch a proof of this. Okay, suppose there were an algorithm. So then I could write a new program and I'll call this program H, that does the following. It tests, okay, so it takes program X, where X is some integer, so, and runs it with input X. And it tests whether it halts or not, using this assumption that we have this other algorithm to test whether it halts. So it either halts or doesn't. So suppose it does not halt on input X. So then after H knows, so it tests this, tests whether program X halts or not, and then H decides to do what the opposite of whatever program X did on input X. So in other words, H halts on input X. You can make a program that will halt if and only if this doesn't halt. I mean, just to clarify, the way that when you run H, what happens? I mean, it doesn't try to simulate program X on input X, because if it didn't halt, that would run forever. Instead, it uses this algorithm that it was assumed to be given, the answer to the halting problem, that tests in a finite amount of time whether this program would have halted if you'd fed it input X. And then, once H knows the answer to that question, H will either enter an infinite loop if it turned out that this one didn't halt, or if it turned out that, sorry, the other way around. So if this program was going to halt, H will enter an infinite loop. And if this program was not going to halt, H will just halt. Okay, so now maybe you can see already that there's going to be what the problem is going to be. So this is supposed to work for all X. So now what happens if you take X equal to H? You can see what happens. You get a contradiction. So we've got a contradiction. So that means that the assumption that there was such an algorithm was wrong.
You can call it program P.
What do you say?
Program P instead of program X. Otherwise, it gets confusing with the input.
Here?
Yeah.
Except I want to have the same X. That's important. So I mean, I've fixed some encoding of programs as non-negative integers so that they have the same type as the input. And you need to have the same X here in order to get the contradiction. Oh, yeah, so the question was, sorry. Well, never mind. Maybe I'll forget the question. Okay. Any other questions? Okay, so from this, or at least using the same ideas, I can now give you a listable set that's not recursive. So this is the result that predated the work on Hilbert's 10th problem, and well, it was important for it. So a corollary of this is that there exists a listable set, so a subset of Z that is not recursive. So okay, so the proof. So here's the set. Take the set of x, the set of integers x, such that program x halts on when you feed it input x. So why is this listable? So I need to. What do I need to do? I need to show you a computer program that can test this condition. That will print out all possible x that satisfy this condition. The program x halts on input x. So here's the program. So for n equals 1, 2, ... do the following. So I have an inner loop, x equals 1 to n, and then for each such pair x and n. This program will simulate program x on input x. But it can't. It better not simulate it forever, because then it won't get to check all the other x's. So it'll only simulate it for n steps. Okay, and if it halts in those n steps, it'll print x. If it halts. So that's if it halts within these n steps. Otherwise, it just gives up and doesn't print anything, because it doesn't know yet whether it would halt or not. So if you think about it for a few seconds, it should be clear that this, if program, the only way it's ever going to print x is if, it won't print x unless it actually does halt on input x. But also, if program x does halt on input x, then that means it will halt in some number of steps. So at least once n is large enough, so that n is larger than x, and also large enough that it's larger than the number of steps it would take program x to halt on input x, then for that n, when you get to this inner loop and get to that value of x and n, it will actually print x. So okay, so that proves that S is listable. So how do you know that it's not recursive? So if it were recursive, that would mean you'd have an, maybe I'll just say it. So is S recursive? I'd like to say that I planned to have this on the board. No. Because if it were, we could repeat the argument in the proof of the halting problem, because this was all that was needed to construct that program H that could not exist. So we could repeat the construction in the proof. So this is the construction of H in the proof of the for the halting of the halting problem. So the name of the proof that the halting problem doesn't have a solution. Okay, so all right, so there you have it. It's a listable set that's not recursive. So okay, so next I'm going to discuss Diophantine sets. So the definition is that, and now I'll consider not just subsets of Z, but also subsets of Z to the n for any n. So such a subset will be called Diophantine. If and only if it's, well, you could say it's the projection of a zero set of a polynomial. So and if you want to use it, say it in terms of quantifiers, in terms of a formula, there should be, so if and only if there exists a polynomial in these variables. So think of the t's as being parameters, and the x's as being the variables that you're trying to solve for, trying to find a solution in. So such that S is exactly the set of parameter values. Let me call it A now. So such that the corresponding polynomial, the polynomial has a solution. So in other words, okay, so when you substitute a value of A of vector A into this polynomial, you get a polynomial in the m variables, in the x variables. And you can ask whether that has a solution. And either does or doesn't. So for each A, so for each parameter value, you'll either have a solution or not. And S is exactly the set of parameter values for which the polynomial does have a solution. So, oh, right. So let's say, right, let's make this a P. Okay, I assume I don't have to repeat that question. That was just, okay, I guess it wasn't really a question. All right. All right, so for example, here are a couple of examples. So first, if you take the natural numbers, and I'll make my natural numbers start at 0. So that's as a subset of Z, this is Diophantine. This is what, I guess this was already mentioned, briefly in McIntyre's talk. So this is a theorem of Lagrange that you can characterize the non-negative integers as inside the integers as those integers that are expressible as a sum of 4 squares. So if and only if there exists x1 through x4 in Z, such that A is equal to x1 squared plus up to x4 squared. So that's a Diophantine definition of the natural numbers. Okay, another example. If you take the non-zero integers, that's also a Diophantine set. So there are many ways to do this. One way is to use the following fact. An integer is non-zero if and only if you can factor it into 2 integers. Such that, so A is factored into B and C, and B is relatively prime to 2, and C is relatively prime to 3. So by this I mean GCD of those, right? So this follows from unique factorization, but now you can re-express this in terms of an equation. This says that exists P and Q such that BP plus 2Q is 1. And so the whole condition you can write as follows. So the non-zero integers are exactly the integers for which there exists BC, PQ, RS such that the single polynomial equation holds. So A minus, so this is a usual, there's a sort of a standard trick. By using a sum of squares, you can convert a system of equations into a single equation. Let's see, C R plus. Okay, so I hope it's clear that if you have a solution to this, it implies these conditions. All right, so another fact I can write down. This is an easy fact, that if you have a Diophantine subset, then it's automatically listable. So actually, I guess I only define listable for subsets of Z, but you can imagine you can use there's an analogous definition that works for subsets of Z to the n. And the proof of this is exactly the same as the proof I gave in the case for sums of 3 cubes. You can write a computer program that will search for solutions to a polynomial equation and print the parameter values for which you get a solution. So okay, but the very deep fact is that the converse holds. So this is the main point of the proof of Davis, Putnam, and Robinson, and completed by Maciejewicz. In fact, this is probably more important than Hilbert's 10th problem itself. But although because this implies, this fact easily implies Hilbert's 10th, the negative answer to Hilbert's 10th problem, but also implies many other things. So, yeah. So, obviously, I'm not going to have time to prove this today. So, I'll just explain first of all why this has the corollary that Hilbert's 10th problem has a negative answer. So in other words, there's no algorithm to decide whether a polynomial has this over the integers has an integer solution. So so this is going to make use of the listable non-recursive set that we constructed using the ideas from the halting problem. So let S be a subset of Z that's listable, but not recursive. So it's listable. So according to this theorem, it should also be Diophantine. So, oops, okay. dPRM implies S is Diophantine. So, okay, so what does that mean? That means that S is a set of S is the set of parameter values for which a certain polynomial has a solution. So such that PA, there's some polynomial P such that if you look at this polynomial and ask when it has solutions, for which A it has solutions, S is exactly that set. Now if the answer to Hilbert's 10th problem were yes, that means that for each A, given A, you could decide whether this, in particular, you could decide whether this polynomial had a solution. So in particular, you would be able to decide whether an integer A belonged to S. So, okay, so so if, let's say, if this had a positive answer, so in other words, if there really were an algorithm to decide whether polynomials had zeros or not, then then we could decide membership in S. Okay, but that's not possible because we chose S, so that it wasn't recursive. So that's a contradiction. So in other words, the answer to Hilbert's tenth problem must be negative. So, okay, so that's all right. So that's the proof of Hilbert's tenth problem. Although I skipped the hard part. So maybe I'll say, just for fun, I'll give one more corollary of this DPRM theorem. So this says that there exists a polynomial with integer coefficients such that if you take it, it's the set of values. So where a runs over z to the n. But you only look at you only take the positive ones. So if you intersect this with the positive integers, then you get exactly the set of prime numbers. So the fact that this theorem, this equivalence, which was originally conjectured by Davis before, about 20 years before it was proved, I guess. It was known before it was actually proved that it would have this corollary, and some people found this corollary so surprising that they didn't believe it, and so they took this as evidence against this theorem. Yeah, but they were wrong. Okay, so in fact, so let me show you how this theorem implies the existence of this polynomial. Okay, so here's the proof of the corollary, assuming the DPRM theorem. So we know that the set of primes is recursive. So, all right, let me call this P. So so P is listable. In fact, P is even recursive. So by this theorem, it implies that this P is Diophantine. So that it can be expressed as the set of parameter values for which it's a set of for which some polynomial has a solution. So there's going to be some polynomial P, little p, such that it's x is a prime if and only if P a comma x has a solution x. An integer solution. Okay, so then here's the polynomial that works. Now I have to be a little bit because I'm working with integers instead of natural numbers. I have to do a little bit of mess with this Lagrange's theorem again with the sum of four squares. But essentially this is the idea. So this is the sum of four squares, comma x. Let's see. So if I take this thing squared and then multiply it by the same sum of four squares, y1 squared plus dot 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 up to y4 squared, and I claim that works. So why does this work? So how can this expression, well, what does it mean if this expression is positive? So the only way it can be positive, well, first of all, this part is already non-negative because it's the sum of four squares. So the only way this thing could be positive is if this thing were positive. But the only way that this can be positive is if this p of, 1 minus something is positive only when this value of p is 0. So this, And the only way that the p can be 0 is if the first argument was a prime. That's how this little p was constructed. So when this value is positive, that means that this is forced to be a prime. But then what's the value of this polynomial at that time? Well, and when this was prime and when x was the value making this 0, this was 0, so this first factor is 1. But also then the second factor was this. So the second factor is that prime. So the value you get is the prime. And, well, that's all you're going to get also. Yeah, so. All right, so, well, if that was too fast, I'm sure you can figure it out on your own. It's not that, okay, it's not that bad. All right, so how much, are we out of time? Or?
More like you can take 5 more minutes.
Okay, maybe I'll just, I feel bad, just leaving this theorem without saying anything about its proof. So maybe I'll just say 1 or 2 or 3 sentences about it. Because that's really I'm not going to say much about the history, but I thought maybe I should say at least what are some of the key steps in this proof. Okay, so here's an outline of the proof of this DPRM theorem. So the first step, and actually I'm doing this completely backwards as far as the history goes, but let me do this anyway. So prove that the following, that exponentiation is Diophantine. So in other words, so A equals B to the C. So maybe think of it as a relation on positive integers, just so it makes sense. Prove that this is Diophantine. So when I say a relation is Diophantine, I mean that if you take the set of triples of A, B, and C in Z cubed that satisfy that, I mean that subset of Z cubed is a Diophantine subset. All right. So actually, this is maybe the trickiest part. This was what Maciejewicz did while using some of the ideas of Julia Robinson from before. What he did was, well, I don't think I can really explain it, but he made use of well, in his original proof he used Fibonacci numbers. You can simplify it a little bit by using other Pell equations. So, but essentially it boils down to you need to use the fact that, so Pell equation is something like this, where D is some positive non-square number, and it's a basic fact of number theory that this is related to units in real quadratic fields, and so there are infinitely many solutions to this. And you can prove various things about, and they form a finally generated Abelian group of rank 1. And using some properties of these solutions, you can somehow build up this. And once you have that relation being Diophantine, you can use that sort of as a subroutine to build up other relations. So it's sort of like writing a computer program where you build up other things. For example, you can write, there's also the binomial coefficient relation. But this you can express in terms of this. And for example, you can use the fact that, so what is A choose B? One way to think about it is that it's the coefficient of some coefficient of x1 plus 1 raised to the power a. And how do you extract that coefficient? Well, you take that. Well, if x is a sufficiently large integer, you take the floor of this, take that mod x. So this is a computer science mod where you just take the value between 0 and x minus 1. So that this holds if x is sufficiently large, so it's bigger than all these binomial coefficients. So in particular, if it's bigger than 2 to the a, then you can write this. So and I'll let you figure out how to convert this into a Diophantine to show that this relation is Diophantine using this. And similarly, you can write down the fact that if you have the bits of, if you have 2 integers, a and b, and you want to say that the binary bits, the places, the locations of the ones in the binary expansion of a are in a subset of the locations for the non-negative integer b. That also you can you can build it up because it happens. There's a theorem from 1852 of Kummer that proves that this happens if and only if the binomial coefficient b choose a is odd. So it's just some elementary number theory. So you can do things like this, and then, well, you do a lot more work, and you show that you can sort of use Diophantine. You can sort of mimic the behavior of any Turing machine using Diophantine equations. You can sort of encode the entire computation of a Turing machine as an integer, and then or maybe a finite set of integers, and then write down equations on those integers that force those integers to represent a valid computation, and then so you sort of encode all computations as Diophantine equations, and that's how you prove the hard part, namely that a listable subset is Diophantine. Okay, so that's the end of my first lecture. So in the future lectures, I'm going to talk about generalizations of the Hilbert strength problem, where I replace Z by other rings and fields. Okay.
Any questions?
Okay, but let me take your picture first. Okay, now I'm ready for questions.
So what's an example of such a polynomial which will generate primes?
You want me to write it down? Actually, it has been written down. I mean, there's a, well, I think they wrote it down in the case of natural numbers, but you can easily convert between, where you only take values where a runs through natural numbers. But using that, by using the 4 squares, you can easily convert between the two. So I know there's a known polynomial. There's a known polynomial in 26 variables that has the property. I mean, so you can write down, you can call the variables a, b, c up to z, and there's an explicit polynomial, and I think I remember seeing it in. I know it's in lots of places, but you can find it written down, for example, in this Hilbert's 10th problem volume from the conference proceedings in the Ghent conference in 1999. It's also in this article by Maciejewicz and Jones from around 1990 or something. I can't remember who originally. Maybe it was Jones and somebody else. I can't remember who actually wrote it down. I mean, it was known that it was known that it existed before people actually tried to write it down, I think. So, yes. You have another question?
Yeah, I was just wondering, did people find the polynomial before Hilbert's problem was completely solved, or?
You mean this polynomial?
For the prime producing polynomial.
No, I don't think people knew what the polynomial was. I think it was just because the construction of this polynomial, you need to use a lot of the ideas used in the proof of the DPRM theorem. It was just known that if it were true they just knew the proof that I showed you, that if this theorem were true, then it would have this consequence.
Mm-hmm.
From the main theorem, recursive implies Diophantine?
Yes, that's right, because recursive implies recursive is stronger than being listable.
Is there a direct proof or easier to prove?
I don't think it's any. I don't think so, because already recursive is already very general. I don't know if it's any easy. I don't think it's any easier to.
Could you repeat the question?
Oh, sorry. Yeah, the question was. So we know that recursive sets are listable, and hence they're Diophantine. So the question was, instead of trying to prove that all listable subsets are Diophantine, suppose you just want to prove that recursive sets are Diophantine. Is that any easier? Can you give a simpler proof of that? And as far as I know, the recursive sets are already general enough that you'd have to go through pretty much all the work in order to prove just even that recursive sets are Diophantine.
So can you give a characterization of recursive sets in the Diophantine manner?
So the question was, can you give a characterization of recursive sets in using Diophantine terminology. So, well, there is one fact that I didn't mention that that's not hard to prove, that a set is recursive if and only if it and its complement are both listable. So using that theorem, you can say, and using the DPRM theorem, you can say that a set is recursive if and only if it and its complement are both Diophantine.
Other questions? Okay, otherwise let's take a coffee break and we'll restart at 11:30 sharp.